Okay, sounds like you can see it. I can see it on your screen.
All right, and off you go.
Okay.
Thank you so much for doing this. Yeah.
Okay. Thank you so much, Michael, for many things. First of all, for inviting me to give this presentation to the club. I'm very, very happy to be here. And I'm very happy that you have the first in-person meeting and I get to be here for that very happy event. I can feel the energy in the room is extraordinary, and I really wish I was here. I was there, but yeah, I'm there virtually. And thank you so much for the description that you wrote on Facebook on the website. Also, that was very nice. I think I'm actually going to take some of those expressions and use them for future because it was very nice, nicely written. And yeah, I think I'm just going to go ahead and start then. Can you still hear me? Okay. Everything went very silent.
Okay, yeah, we just had a little interruption, but I think we're okay.
Okay. I will, right, okay. So yeah, my name is Ioana Zelko. I've worked with my PhD advisor at the Center for Astrophysics at Harvard University, Doug Finkbeiner, and I will mainly tell you about my work from my PhD. And I just wanted to give a shout out to the Amateur Astronomy Club. This is also where I got my interest in astronomy back when I was in Romania. I had a good chance of meeting some super awesome amateur astronomers who taught me a lot about astrophysics in high school, and that really motivated me to study it in college, and that led to me doing my PhD and research. And yeah, I'm just going to go ahead and start. So I will aim to give some background information, then summarize briefly results from 3 projects I worked on, and then conclude. And I just wanted to specify that my goal was to sort of have a 15 minutes, 20 minutes introduction that hopefully everyone should follow. And then when I get into the nitty-gritty details of the projects, I have sort of condensed a lot of the details of the methods, and they're a bit skipped over because time is limited. So don't worry if you feel like some steps are not very explicit. It was a bit of on purpose decision. So a lot of the methodology actually is not very walked through in detail. But if you have any questions about particular anything actually, you can feel free to ask me today or email me. Michael has my email information. I would be very happy to answer anything and give more in-depth answers. So the thing that makes me very excited about astrophysics is that I feel like at the core of my work I get to think about fundamental questions about our universe and what we are trying to find the answers to. So such questions are what is the universe made of, and what are its properties, and how did the universe form and evolve. So these fundamental questions are the backbone and the motivation for which the the research is funded, and this is kind of the end game, holy grail, eventual answer. But actually, in my research, I focus on something a very tiny contribution that eventually can help answer some of these big questions. But locally, it's a very tiny step towards improving any of these questions. So as we all probably have heard before, the speed of light is finite. And what this means is that when we look at the sun, for example, which is quite far away from the Earth, it takes light 8 minutes to get from the sun to us. So actually, when we see an image of the sun, we see it as it was 8 minutes ago. And if we look at an object that is even further away, such as the Andromeda Galaxy, which is a companion galaxy to the Milky Way, which is located 2.5 million light years away. Light travels for 2.5 million years before it gets from Andromeda to us. So when we see a picture of Andromeda like the one here, we're actually here seeing Andromeda as it was 2.5 million years ago. So that's quite a big leap in time to be able to see, using our technology. And basically, the further we look in distance, the earliest in time we get to observe. And we can look so far away that we reach times when galaxies and planets have not yet formed. And we can see sort of as early as possible, as early as possible in the evolution of the universe. And turns out that this earliest moment that can be observed is this primordial soup of particles that radiates and becomes opaque in our detection. So we can't see beyond it. So this is the final sort of frontier that we can detect observationally, because that's the farthest point that light can travel to us from. And this radiation is very important because we can constrain different evolutionary models for the universe by studying it. And we can get a glimpse even of details that happen before before this radiation by looking at its properties, such as validating the Big Bang theory, also known as the inflation theory, which is still a theoretical theory, and a theoretical theory, so it's just a theoretical result so far. So it needs to be experimentally validated, and the way to do that is to study this radiation in very high detail. So the cosmic background radiation was first discovered in 1965 by Arno Penzias and Robert Wilson, which used the Horn antenna at the Bell Laboratories in New Jersey. But the results were jointly published in 2 papers, one experimental by them and one theoretical by Robert Dickey, Jim Peebles, and David Wilkinson, which provided the expected interpretation for the radiation and linked it to the thermal early history of the universe. And this was, the theoretical trio famously remarked that they were scooped because they had just at the time thought of funding an experiment to look for this radiation, exactly as Arno and Robert were struggling to understand this noise that they were seeing at 3 Kelvin in their data. And luckily, through an MIT professor, they were put in contact, and they were able to provide this joint release of both data and theoretical interpretation. So Arno Penzias and Robert Wilson were given a Nobel Prize for this discovery in 1978. And Jim, I think it might be Pebbles. I don't want to mispronounce. I think I'm mispronouncing his name. Was also given a Nobel Prize in 2019 for a variety of theoretical cosmology contributions, and this one included as well. So after their measurements in 1965, new generations of measurements were made in order to characterize the cosmic microwave background better and better. And it was the COBE satellite who mapped the spectral distribution of the radiation coming from the cosmic microwave background. And for this measurement, Joan Mather and George Smoot were given the Nobel Prize in 2006 for their um, work on the Kobe satellite, which included the discovery of the anisotropy of the CMB across the sky, but also the characterization of the black body form of the radiation. So by this term, the black body radiation, they refer to the function of the emission in frequency space that the radiation takes, which is a satellite shown to be this. So a black body spectrum is described by what we call a Planck function, shown here on the right. And an interesting thing about this function is that it's a function of a single parameter, the temperature, even though it looks a bit complicated. So on the left, you can see the effect of turning this temperature up or down. So basically, as we increase the temperature, we get higher overall amounts of radiation coming from the body, but also the peak of the radiation shifts towards higher and higher frequencies and lower wavelength. So if as we look into the electromagnetic spectrum, basically we can see the radiation peak swiping the spectrum as we change the temperature of the so-called black body from low to high. So the question that one can pose is, what can cause a perfect black body radiation to not be a black body anymore? So we know that the cosmic microwave background was a black body at the beginning, but is it going to be a black body when it arrives to us on the detectors? And what kind of processes do we see affecting it? So one first phenomena that we need to think of is the redshifting of the radiation. So the universe, as time passes, is expanding, and we use the redshift parameter Z to parameterize its expansion. So as it turns out, a black body radiation distribution remains a black body radiation as long as equilibrium is maintained. So just by the expansion of the universe, the cosmic microwave background would not change its black body radiation, from when it was emitted until it reaches us. But what will happen to it? So even though it will still be described by a Planck function, is it will have a temperature that is shifting, and this same temperature is being cancelled by, so that the change in temperature is being cancelled by the change in wavelength, which is why the analytical form remains a Planck function. But what was originally a 3000 K emission, thermal emission, by the time it reaches us, because of the redshifting of the radiation, it becomes a 3 Kelvin emission. So this is the radiation that sometimes with all earlier versions of the TV, the ones that had antennas, you could see those the kind that had those dipole antennas. You can see those black and white spots appearing when you had no or you had no channel signal coming in, and about 1% of that black and white noise was coming from the cosmic microwave background itself. So I get really excited when I realized that as a kid I was actually seeing the effect of the radiation on my own TV, if only to 1%. But there are processes that maintain the temperature equilibrium of the system, which is the condition required for this black body radiation to be maintained. So when these processes, like the double Compton scattering, decrease, we can see injection of energy that will lead to spectral distortions. So the double Compton scattering is a process that allows the creation of new photons. If we don't have the creation of new photons happening, when we inject new energy, we conserve the number of photons, and they have to go to higher energy through to the injection of new energy, and that leads to departures from the temperature equilibrium. So, because if we wanted to maintain equilibrium, we would need, if we get new energy, we would need to get new particles as well to be able to absorb those energies and maintain the amount of energy per particles. So these departures from the equilibrium of a black body radiation happen when these temperature equilibrium processes are no longer able, they decrease and are no longer able to account for to redistribute absorption or loss of energy in the system. So at earlier times of the cosmic microwave background, we see energy injected, and we get distortions that are characterized by what we call the chemical potential mu. And those are called mu distortions. And later, we see electron scattering photons, which produce what we call the Y distortion. And these distortions are proportional to the electron density, but also to the temperatures of the electrons. So if you're familiar with the Sunyaev-Zeldovich effect, that is a type of a Y distortion that happens later on in the game when the density of the electrons are small because are high because the matter clumped over, but the temperature is low. But we can also see Y distortions at the beginning when the density is low, but the temperature is high. So basically, throughout this history of the evolution, we get these distortions happening either before the CMB or after the CMB was emitted. So they leave an imprint on the spectrum of the cosmic microwave background. And what has been done so far was that the FIRAS experiment and the COBE satellite was the last major satellite to target the frequency spectrum of the CMB. So there have been many missions that have studied the variation of the CMB in the sky directions. And these are, WMAP, Planck, and they talk about spatial anisotropies of the CMB. So how does the temperature of the CMB vary in different directions across the sky? But what I'm talking about here are the spectral variations in the CMB. So how does the spectrum of the CMB over many frequencies change? So these are different kinds of anisotropies. They are spectral anisotropies. And no measurement has been done since the COBE satellite of these spectral distortions. So at the time when COBE was made, the results showed that within their error bars, within their noise limit, the CMB was described by a perfect black body. They couldn't detect any departure from the black body radiation. And as you can see through this curve, it matches perfectly the points of the observations. And the error bars are present on the top panel as well. They're just so tiny in order of magnitude that they can't be seen with the eye. And they are shown below in the second plot. Because the order of magnitude is just so different. But because it has been many years since that measurement was made, now we have technology that could allow us to remake this measurement at much higher signal to noise. So there's hope that we could be able to actually get to the point where we can observe the Y and mu distortions of the cosmic microwave background. So there are missions in proposal stage by NASA and ESA as well on the European side, which would create mission targeting the spectrum of the cosmic microwave background at 400 frequency channels, spaced 15 gigahertz, apart. So this is a very fine measurement of the cosmic microwave background, like a tiny steps, which integrated over years of measurements with high precision detectors would get the signal to noise to big enough values that you could get wide distortions. So these missions like PIXI, the Primordial Inflation Explorer, are in proposal stage. They have had white papers written about them, and right now they are being proposed for the MIDEX category at NASA. And I hope eventually in the next couple of 5 years or so, they will be funded and hopefully fly in the next 10 or 20 years in the long term. So the error bars and that these new missions are capable of reaching offer order of magnitude improvement on the detection of the Y and mu parameters. So basically, PIXI, a satellite like PIXI, would like to make a ridiculously precise measurement of the spectrum of the CMB, so precise that it would be able to get at these spectral distortions, which are very, very dim. So the tough part of the problem is that there are other things in the universe that produce radiation. And when we put a detector on a satellite in the orbit around the Earth, the detector is going to capture all of these radiations simultaneously. And we need to be able to understand the radiation in very great detail to be able to remove it and get to the fundamental, CMB science that we want to do. So the primary goal is to make sure we can check that the signal can be extracted from the foregrounds. So for our experiments, it's not backgrounds, but foregrounds that are in front of the cosmic microwave background, as the universe evolved, that we need to take care of and remove. So there are many different radiation sources that overlap with on the sky together. But for the ones that are the most impactful for the CMB science are the radiation coming from the interstellar medium dust. So dust, much like the human's body as well, radiates thermally, and this thermal radiation goes into the infrared and microwave, and it overlaps over the CMB. And also we have dust in other galaxies as well. And the total collection of radiation coming from dust in other galaxies is called the cosmic infrared background. So this is just dust in other galaxies radiating thermally, and it gets redshifted based on the position of the galaxy, and then it reaches us. And then we have the synchrotron radiation given by highly relativistic particles getting bent in the magnetic field of our galaxy. So this produces a synchrotron radiation, as well as the free emission, which is also free electrons changing the energy of photons. And we have spinning dust emission as well as other processes. And in my research, I focused a lot on the interstellar medium dust, but as well as studying it in the presence of the other foreground as well. And kind of being able to, I was hoping to be able to ask the question of how impactful will the interstellar medium dust be on the measurement of the YMU distortions, and can we remove it properly to be able to measure the distortions? So, sorry, 1 second. So if we look, one thing I really like about interstellar medium dust is that we can see it with the naked eye. So this is a picture I took with exposure that mimicked the seeing from the view that I had from my own eyes when I went to the Blanco telescope in Chile. So I was just taking a normal picture outside of a telescope, but the sky was very clear there. So when I was looking at the galactic plane, as you can see here, you can see that there are dark spots on the galactic plane, like here, and that it is not homogeneous. So these dark spots are clouds of dust. And if they were not there, we would be seeing the galactic plane much more homogeneous in terms of distribution of stars. So this inhomogeneity that we see in the galactic plane is given by the interstellar medium dust. You can see here with this patch picture that was created from multiple exposures, just in optical range. We can clearly see the dust structure of the clouds. And while it is very obvious that there's dust in the galactic plane and it's very thick, there's dust outside of the galactic plane as well, all over the sky. It's just not as thick as it is in the galactic plane. So how do we characterize the interstellar medium dust? This is a question that a lot of people have thought for a long time, including myself. So unfortunately, we can only characterize interstellar medium dust mostly indirectly because we can't really go get a sample. Though one can try and send a mission, such as the Stardust mission, which was sent to a nearby comet to collect the specks of dust. So as the mission was going on, they had this aerogel pictured here on the right, which was well, the plan of it was to be hit by dust particles that were traveling very fast and captured in the aerogel. So in theory, one could take these captured dust particles and find out information about the composition of dust. But this kind of a method would not, would kind of self-select for the dust particles that are traveling very fast, and it would not give a good view into the distribution of the sizes of the dust grains. So most likely, all this information needs to be, obtained remotely by matching or far observations of the dust with laboratory experiments for dust. So there are two very important ways of characterizing dust. One is through its extinction and one is through the emission process. So dust blocks light coming from behind it, as it can be seen in this picture of the Barnard 59 dust cloud, where the dust just opaquely blocks the light of the star field behind it. And the other process that's very important to us is the thermal emission from dust. Much like we as human bodies emit radiation, our radiation peaks in the it's mostly emitted in the infrared, which is why the army can see us through buildings if they really want to, using special goggles. So do dust grains. they also emit radiation. And if we compare the dust radiation with the human radiation, the dust is much cooler than the body, so it is not as bright, and the peak of it is at longer wavelengths, and it is much much less brighter than the sun, or but unfortunately it is also much more brighter than the universe, or what we call the universe. We refer to the CMB here, which is radiating at 3 Kelvin. So as we said, because the higher temperature means higher radiation, higher amount of radiation that can go between 30 Kelvin, even up to 50 Kelvin temperature. So 18 Kelvin or so. So that's much higher than the universe temperature of 2.7 Kelvin. So as you can see between the red curves and blue curves here, it is much brighter, but a bit shifted compared to it. So this is a map from the Planck satellite of the 857 gigahertz frequency band from the satellite. So a satellite like the WMAP and Planck, they map the entire sky at chosen frequencies, but very few frequencies. So they have 5 or so frequency bands that they choose, up to 8 actually in the case of Planck, and they can they map the sky at high precision. So at 857 gigahertz, dust is the dominating foreground. So basically, you can literally see the amount of dust radiation by looking at this frequency. So because dust is hotter than and much brighter than the CMB, it is, and the CMB itself, it is 10,000 times brighter than the spectral distortions that we're hoping to detect. So let's keep in mind that the spectral distortions probe processes that perturb the cosmic microwave background, and these processes are, can be dark matter annihilation, primordial black holes, and also just the interaction with the reionized medium as the universe evolves, all of which are very important physically and can provide a new window into how we're able to study the universe and how we're able to infer. So in the long term, this is a very important tool that we can sort of use to get at these processes if we're able to characterize these spectral distortions. But unfortunately, they are 10,000 times smaller than the CMB, and the CMB itself is much more than the foregrounds. So this becomes a very challenging measurement, where you have to extract this tiny signal that's 8 order of magnitude smaller than the other radiation that you're already having in your detector. So to characterize dust, as I mentioned, we use extinction observations and emission spectrum observations. And throughout the last decades, there have been studies showing that you can characterize the function of the extinction of the dust by using a parameter called RV. Intuitively, you should think of it as sort of controlling the slope of the extinction function. And for the emission spectrum of the dust is complicated because we have multiple types of dust grains of different sizes and different compositions, kind of integrated along the line of sight, and they emit together. So what Planck satellite have done and other people have done is they model this emission spectrum using a modified black body emission for the dust. A modified black body is just a Planck function, which is a black body function, multiplied by a power law, which we call frequency to the power of beta. So that's how we get the three parameters: tau, beta, t. T is the temperature of the black body, beta is the power law, and then tau is just the overall optical depth of the emission process. So, but in reality, we know that this radiation is more complicated than that, and analytically, it should not be modeled by just the simple modified black body. And but the advantage of modeling the modified black body is that it's an easy three parameters only model. So when you have to analyze data and you have to remove the dust, when you only have three parameters, then you can, you create less noise in the other parameters that you're trying to detect by having only three. But however, if the modifiable body is too simplistic, you are left with residuals from the model when you're fitting, which can be disastrous and create biases in the end result. So my goal was to understand what should be the appropriate modeling and how complicated can we make the modeling. So to get at this problem, I used a result that was published in 2016 observationally that showed that there exists an anti-correlation between the RV parameter, which is an extinction parameter, and the beta parameter from the emission of the dust. So this anti-correlation was unexplained. As I was studying the foreground for the peaks emission, I tried to see if I can explain this anti-correlation, like what could be causing dust to have this anti-correlation property, because these processes, the extinction and the emission property, physical processes, are happening at very different wavelengths. So there was no direct intuition as to what could be, what could be causing this. So in my research, I started from a size distribution model from Weingarten and Drain. So this size distribution model allows us to be able to tune how many particles of a certain size in dust, we include in the model, and what kind of dust do I use, mostly silicates or carbonaceous grains or polycyclic aromatic hydrocarbons. So I have these three types of dust grains in my model, and I'm able to configure, what size of grains I put in and what kind of composition they should have. So what I do is I constrain these models using physical extinction functions that we know the dust grains should have collectively. So for each proposal of a distribution of dust grain model, I was checking to see how it compares with the actual, how its extinction over frequency, compares to data, and making sure it's tied in, using a Monte Carlo chain method. And to calculate the emission of the collection of dust grains, I calculate their equilibrium temperatures. So dust stay in a bath of radiation coming from the stars in the galaxy. So as they are sitting in this radiation bath, they get heated up and they emit radiation. Basically, that's what's happening. And to calculate the equilibrium temperature, because assuming they're in equilibrium, we have to say that the power in, which is the power absorbed by the dust grains, is equal to the power out, the output power of the grains. So using my model for the interstellar radiation field, I calculated the equilibrium temperatures for each type of grains and for each radii of the grains. So now I'm ready to calculate the emission spectrum. So this allows me to calculate a more complicated emission spectrum than just a modified black body, because it's a spectrum of dust emission that is more informed by the the properties of the dust, not just an approximation using 3 parameters. So I obtained this intensity by summing over all of the dust of each size and composition, and assume the dust itself radiates as a black body, and also multiply it with an absorption and emission cross section. So this is where the equilibrium temperatures of the dust come into play. So in this project, I was able to see that by tuning up and down the volume, the ratio between the volume of the silicates and the volume of the carbonaceous grains, I'm able to actually reproduce this anti-correlation. So this provided the only result so far, the only explanation so far of this anti-correlation, which is, it could be caused by the fact that dust has more silicate than carbonaceous grains in certain parts of the sky. However, I should mention that this is just the model. So it's very dependent on the model that we use for the size distributions and for the optical parameters of the dust and composition. So if one comes out with a different model for a dust, different conclusions might be able to be there may be other explanations for this result as well. But nevertheless, this was very happy time because it gave us more confidence that this anti-correlation measurement is real, because when we have a theoretical explanation for it, is also good news. So like I said, I determined that volume functions that depend on RV for between silicate and carbonaceous grains can give us this result. So coming back to the dust foreground subtraction, by doing this analysis and figuring out this anti-correlation, I was also able to obtain a collection of dust spectral energy distributions, which were physically tied by the extinction functions. So they were both very varied in the models, but also physical. So dust foreground subtraction is difficult because it varies across the sky. So these properties of the dust vary across the sky, and they also vary in frequency. So we can't just assume that dust emission is the same. It is the same in one frequency, and then take the mapping that frequency and remove it at the others. So having this collection of emission of dust models that I have just obtained, I can ask the question of how do these dust emission variations overlap with the spectral distortions I'm hoping to detect from the cosmic microwave background. So when I look at my dust emission, which is this blue-green line, green lines band, this is the entire band. The green one includes variation in the interstellar radiation field, which heat up the dust, and the blue collection is with that radiation field kept constant. And what we want to detect are the pink and purple lines, which are the Y and mu distortions. As we have the other foregrounds like the synchrotron in red and the free in green and the cosmic infrared background in orange. So what I was trying to find out is how can I characterize and how much variation is there in the actual dust foreground here, and how does it overlap with the spectral distortions? And even though by eye it might seem that the functions are very different, because the orders here on the left is a logarithmic plot, so the spectral distortions are actually much fainter than the dust in certain areas. So this variation in the band can be very important and could cause unconstrained parameters. I use a tool that is called principal component analysis, which has nice name, but it's actually a very simple principle. So just as a very brief tutorial, if we had a resort and we wanted to measure to find out what physical law describe this resort and ball that are moving, and we use 3 cameras, and we put 3 cameras on the system, and we see this ball moving, and we record this ball moving up and down, up and down on the floor, as the resort is moving. So what data we obtain from these cameras is 3-dimensional positions from from each of these cameras, right? So we have a lot of dimensionality in the data, but actually the physical law that describes this motion is a single-dimensional law. It's just K delta L, right, for the resort. So the principal component analysis allows us to take a data set that is highly dimensional, in this case, the measurements from all the camera angles, and create a matrix out of this data set and calculate its eigenvalues and eigenvectors, and basically transform the matrix to a different basis. And in this basis, we can see how many directions in a data set, how many dimensions are important. So it will show us that one direction in the transformed data set has a big variation, which is the one containing a signal, and the other ones are just the noise in this case, because it's only one dimension that matters. It's a single dimensional physical law for this experiment. So similarly, for my research, I had these spectral energy distribution functions, which were basically a 416-dimensional data set, because I had the information for each frequency channel for the emissions functions. And my question was, is it really a 416-dimensional data set, or can it be transformed to a much lower dimensional, physical process, and we can characterize dust by in a simpler way by not using 416 dimensions. So these are the principal components for the spectral energy distributions for the dust, and these are the first 20, and I only took the first 20 of them because their contribution to the importance in the modeling the emission decrease as the number of components increases. So it becomes irrelevant to include more than this. So these components basically allow us to overlap them linearly together with the right amplitudes and recreate any spectral emission distribution from the original data set that we started from. So basically, you can decompose any SED on these principal components and then recreate it if you want. So I use all of these components together with the measurements, together with the functions for the spectral distributions, to see just how much does the sensitivity to the Y and mu distortions degrade as a function of the complexity of the dust model. Can I pause for a second and ask here, should I go until 4 or 4:15, or kind of what's the timeline?
I think we're getting close.
Okay. Okay, so I'm just going to take 5 more minutes then to go very fast. So what I discovered was that by including all of the principal components, the sensitivity for Y and mu only degrades by less than an order of magnitude. So basically, by modeling dust in this more complicated way, it will not be game problem for the spectral distortion measurements, which was a great news. So the sensitivity degree less than an order of magnitude. And I also looked at the combinations of the other foregrounds, and I could see that there are, they have, by turning them up or down, we could see which one of them causes the most amount of impact, and it was the synchrotron that has the most amount of impact on the measurement. But also, the bad news is that if we model all of these foregrounds without any information from other X satellites, it's not enough. Like the sigmas and the mu become larger than the fiducial value for the mu distortions if all of the foregrounds are included. So if Pixie wants to detect the mu distortion, they will need to have another data set from another mission to be able to determine the mu distortion. So at least one of the foregrounds needs to be put constraints on from another mission in order for this to happen. I also looked at the model discrepancy error between the modified black body and the SEDs, and basically determined that it's really important to not model the SEDs using a simplified black body function because it creates offsets in the Y and U parameters. And I looked at the cosmic infrared background analysis a bit, but I think I can skip this part here. Bottom line is the cosmic infrared background is very complicated as well because it's caused by overlapping of dust properties from different redshifts. And it should also have basically a data set that would characterize it better. And finally, I looked at the CMB shadows, which is the absorption of the CMB itself by the dust grains. So far we were talking about the CMB impact by dust emission or emission for these foregrounds. But in 2020, there was a paper that showed that actually the absorption of the CMB by the dust or other foregrounds is also important for, they were talking about the anisotropy of the CMB measurements, but in spatial directions. And here in this paper, I looked for the first time to see how the CMB shadow, what we call shadow, it affects the spectral distortion measurements. And the conclusion is that it's very important to include it, otherwise we're going to have really bad biases. So in a current and future work, we would like to see what foreground measurements are available from future missions that could be used to make spectral distortions detectable. There's hope that we could be using the CBAS dataset to get at the synchrotron, or create an SED collection using SphereX, or make a dedicated dust mission using dust busters. The current project I'm working on is a 3D 3π dust temperature map around the sky. So for this kind of map, a three-dimensional map could be used to reconstruct polarized maps, to tie them with magnetic field radiation in the galaxy. And if we know where the stars are in the galaxy, we can also estimate the radiation field of the stars if we know the temperature of the dust grains. So it will be a very interesting thing to have. And what we already have and I'm building upon is a three-dimensional dust reddening map, which is seen here in this video made by my colleagues. So basically by studying extinction and by pinning down the amount of extinction along the line of sight, my colleagues were able to create this three-dimensional map of the dust. And what my project was in the last half a year was to put temperatures for these dust grains at different distances. I basically tie the dust emission to the two-dimensional maps from Planck, but model it in 3D. And I obtain, I reconstruct the maps in 2D from the 3 dimensions from the emission maps, and they work well. And basically I obtain these temperature sizes for the dust at different distances. So this is temperature at 0.20 kiloparsecs, and then as I move, I get different temperature for the dust. And the farther away I'm in time, in distance, the less constraints we have on the high latitude because there's less dust over there. But nevertheless, it's a very interesting thing to have, even if it's just lower latitudes. And I also looked at the Cepheus cloud, which is a dust cloud that is made of two components. And we can see these two components by looking at the extinction. And we can see there's two jumps, one here, and this is like basically the edge of a cloud, and then another cloud appears, which makes another jump in the total extinction functions. That's how we are able to say that, along the line of sight, there's two components to this dust cloud. So I was able to model the temperature of this dust cloud and show that the first component is a bit hotter, it has 20 Kelvin, and the second component has 18 Kelvin. So this is a sort of first determination of three-dimensional temperature of a dust cloud. So in conclusion, the first project was about describing the explanation of the carbonaceous of the RV beta correlation, and gave us the possibility that it could be the ratio between carbonation and silicate volume priors that could basically give this anti-correlation. And it also allowed me to create this spectral energy distributions for the dust that are more closer to reality, which I could then use in the spectral distortion analysis as a foreground to study to see how the sensitivity to Y and mu degrades. And then finally, I mean not finally, then I analyzed the combination of foregrounds and determined that we need at least one more tie-in for the foregrounds to be able to detect the Y and mu distortions, and calculated the discrepancy between model ACDs and modified black bodies, and then performed the cosmic infrared background analysis in the shadow analysis. So for the third project that I just described very fast, I successfully reconstructed the 2D emission maps from the 3D reddening. So the reddening maps are just extinction maps, basically, of dust. So this is more like a proof of concept, three-dimensional temperature map, because the resolution is sort of very small in distance, but future generations of the extinction maps will allow us to get to much better temperature maps as well. And I calculated the three-dimensional temperature to the Cepheus cloud. So thank you so much for having me here, even if virtually. And if you have any questions, please feel free to ask. I'm going to stick around for a while here. And I'm just going to leave you here with a picture I took at the Blanco telescope, because I think we have a lot of sky picture fans here. What I really like about this picture is that I can see the valley and the stars at the same time, because I did a trick. And I'm wondering if you guys can figure out what the trick is here. And it is a single exposure picture. There's no overlapping of images. And the trick is that the sky night is so clear, and what we see on the right is the moon and not the sun. And the moon is lighting up when I expose for I think 20 seconds, I expose the picture. You can see the valley lit up just by the moon, and then you can see the pictures. Cool. So yeah, that's it from me.
Okay, thank you, Ioana. I think we have a question. Bill?
Yes. Hello, wonderful talk. I have a question that goes back to the original spectrum from Kobe, that perfect black body spectrum. And I would like to ask you whether there is any hope for that spectrum to be resolved into features. You mentioned there were these certain distortions, and so that's one part of the question. Will these distortions ever be resolved? But also, why not spectral lines like what you would see from stars? Because the cosmic microwave background is basically arising from a surface of last scattering so too, the spectrum from stars are arising from surfaces of last scattering from their photospheres. And so, why not see red-shifted hydrogen lines or, calcium lines, like what we see in stars? Now, I asked this question to Mather a long time ago, and he just said, no, it's all going to be perfect black body. So,
Gabriel.
do you have any?
Yes. So right. So in stars, you see the hydrogen lines because you still have hydrogen in the star itself. But in the CMB, it's too hot to have hydrogen there. So there's no hydrogen formed there because it's too hot, like to have the atoms sticking together.
Okay.
I think that's why he said for sure you will see. That's why you can't see that.
The temperature is supposedly around 4,000 Kelvin. That's very similar to the photosphere of a star.
That is true. That's a good point. Let's see. Yeah, it's a good point. But that's what I knew. Yeah.
You're in good company.
Say again, what?
You're in good company with Dr. Mather.
Yeah. I wonder if the density is not the same though. Because I think the stars are more dense than that at the time. I think it's like by the time it gets to 3,000 Kelvin, because it's not 3,000 Kelvin at the beginning, right? But by the time it gets to 3,000 Kelvin, the density may be like they could be too hot and too far away. That's my intuition, but I'm gonna think more about it.
But
I do know that they are not formed though. So like, why are they not there? That's the answer is because they're not there. But
Yeah.
why are they not there is the question.
it's possible we have yet to resolve it. And so that goes back to the distortions, which might be easier to resolve. Do you see a hope of actually resolving those distortions that you mentioned, the mu distortions?
Yeah, for sure. So this was kind of a happy kind of result from me is that we expected the dust to have, so when I looked at this kind of more complicated models that were accounting for the difference in dust, sizes and compositions, I expected we kind of intuitively thought it might be a gain killer, but it turns out it's not, because just an order of magnitude increase is not a problem especially for the Y distortion. So I was talking about how the mu distortion won't be detected, but the Y distortion is 1,000 times has a 1,000 times higher signal to noise. So for sure, if they make the Pixie satellite, they are able to get the Y distortion at least average across the sky, which would be pretty cool as well. But they might even be able to get it without averaging across the sky. So they might be able to get it to the resolution of the mission, which is about 2 by 2 degrees, across the sky. And this is just intuitively what I've been told happened, like, when they were making WMAP and they were making other satellites, like by the time they have the satellite actually built and made, we will know so much more about how to characterize the foregrounds, because other data sets are coming in. So for sure, like Y can be detected, and depending kind of like when the mission will be made, we will probably be able to detect mu as well. And then the interesting thing is how to detect, like, these distortions, but like at different times in the evolution of the universe. And that's kind of next level, like next level precision. Like, can you distinguish between these different emissions overlapping together?
Thank you.
Yeah.
Jim Nordhausen, you had a question? Turn on your mic.
Yes, does gas have an effect on the signal or just dust? And second question is basically, is Pixie going to be like a microwave spectrometer rather than discrete frequencies like South Pole Telescope and other instruments?
Right. So gas does not have a significant effect compared to dust. Dust is the main contributor here. Yeah, that's basically. And then so Pixie will be different than the South Pole Telescope because the South Pole Telescope targets a couple of bandwidths and then integrates over those bandwidths. So it has it has a particular bandwidth and then it integrates over it. Pixie will have 416 frequency channels spaced 15 gigahertz apart. So they are linearly spaced you get 416. So it's quite a different beast, and it would be super nice to have both, and you can complement things. But the downside compared to the South Pole Telescope and the other experiments that do the bandwidth is that the resolution is much lower. So you get resolution in on the sky. So you get much better frequency resolution, but much less on the sky. That's yeah.
Mario?
So the Pixie, can you hear me?
Yes.
Okay, great. The Pixie satellite, you said, spins once every 4 minutes. I imagine that's done for temperature control. But then how are you taking a precise measurement? How are you integrating on your detector?
I did not know that. Sorry.
Remember, it's 3 in the morning there.
No. I just I'll ask Al Kogut who's doing the building of the stuff, and I'll get back to you.
Could the spin be related to polarization measurements?
No. So Pixie can spend time. It has two modes. It can. So today I described to you the mode in which is targeting absolute intensity measurements, basically. So this absolute intensity is just integrating the emission along the line of sight, along the line of sight. And the other mode is the polarization mode. I don't think that's how they, because they're not necessarily simultaneously. They have to be in one and or the other. So when they're doing it, so it's not the polarization mode that helps us. But yeah. Well, yeah, I shouldn't say what I think. This is just what I think. I don't know. This is the answer. I have my guess, but I don't like guessing. Okay.
All right, do we have any other questions for Ioana?
We have other questions in the chat?
Yeah. I guess I misspelled it.
Yes.
If you would just ask rather than type them, that would help.
So someone is asking, do the peaks and valleys in the Kobe residuals have any significance? Let me get back to it. I think you were seeing oh, actually you're not seeing my screen anymore, are you? Let me just turn it on.
Oh, yeah, share your screen again.
Yeah, sharing, okay. These are the residuals from Kobe. The Y and blue, the red and blue lines here are the analytical fiducial values for Y and mu, just for comparison. They are not fixed to the data or anything like that. It was just like, it's just, they plotted it to show that when you are in the same range as the residuals, and thus not detectable. But I'm not sure I see a significant peak or valley in the race.
Okay. Can you hear me?
I can hear you, yes.
Oh, okay, good, good. No, if you look at what I'm seeing, and I assume those dots that you have, and I'm sorry I misspelled Kobe, I was thinking of Japan. But if you look at the air bars, it does look like they significantly deviate from the baseline, at least in some cases. And I was just wondering if that was, if there was some interference, or if there was any, if that was just sort of randomness, or if there was actually a signal in that, in any of that. Because, like, for instance, you notice, like, right in the middle, there's actually one air bar that's actually seems to be at least a couple standard deviations off the
From
baseline.
zero. I see. Yeah, I do not know that. I'm gonna have to look into it.
Okay. It just was curious because it actually kind of relates a little bit. I don't think it's really, it just seems, it sort of jumped out at me, and I was just wondering if there was something there.
Yeah.
It was kind of a very, should we say, a very a rapidly changing sort of change versus what you see with these distortions, which are very, very gradual, kind of, I guess, broader band type distortions.
Yeah.